This is Bob Capetta, and this lesson is linear programming with graphing, minimization. So we're going to look at a minimization problem this time. So here I want to minimize the following. Minimize z equals 10x plus 12y. Subject to the following constraint equations. 3x plus y greater or equal 10. X plus 2y greater or equal 10. X greater or equal 0. Y greater or equal 0. And as before, x greater or equal 0, y greater or equal 0 tells me that this restricts everything to quadrant 1. So this will be defining line 1. This will be defining line 2. Let's go ahead and graph those two. Let's find our feasible region. Check for the corner points and then test the corner points to see which one gives us the minimum value for 10x plus 12y. So we're starting with 3x plus y greater or equal to 10. And I prefer to graph these using intercepts. So here's x, here's y. If x is 0, what is y? If y is 0, what is x? Plugging in 0 for x. 3 times 0 plus y equals 10. Remember, we're going to solve the equation. 3x plus y equals 10. This is our first line. So 0 plus y is 10, so y is 10 here. If y is 0, I get 3x plus 0 equals 10. 3x is 10. X is 10 thirds. Which is a little bit more than 3. So if we want to graph this in the first quadrant, y goes up to 10. X goes up to 10 thirds. So just a little bit more than 3. So the line in the first quadrant will be this. And we're going to check to see which way we shade. So we're going to check 0, 0, our favorite point. So we're going to test 0, 0. To see which way this is going to be shaded. So we have 3x plus y greater or equal to 10. Plugging in 0, 3 times 0 plus 0 greater or equal 10. 0 plus 0 greater or equal 10. No. So we're not shading towards 0. We're shading away from 0, 0. So this is our first line. It's our first line again, away from 0, 0. As we're collecting the information we need to prepare to determine our feasible region. So that's our line 1. Let's go ahead and do line 2, x plus 2y greater or equal to 10. And again, we solve it first as an equation, or graph it first as an equation. X plus 2y equals 10. We look at intercepts. Here's x, here's y. X is 0, what is y? Y is 0, what is x? If x is 0, 0 plus 2y is 10, 2y is 10, and y is 5. If y is 0, x plus 2y is 10. X plus 2 times 0 is 10. X plus 0 is 10. X is 10. So this is our line 2. And we want to see which way we're going to shade. So we're going to need to test 0, 0. First, let's go ahead and graph this. So up to 5, 1, 2, 3, 4, 5. out to 10. 1, 2, 3, 5, 6, 7, 8, 9, 10. I just about can make it. So we're looking at the first quadrant portion again because we said x is greater than 0. Y is greater than 0. Here's my point 0, 0, so we're going to test 0, 0. So our original is x plus 2y greater or equal to 10. So 0 plus 2 times 0 greater or equal 10. 0 plus 0 greater or equal 10. 0 greater or equal 10. No. So we're not shading towards. Again, we are shading away from 0, 0. So we're shading away from 0, 0. So we have these two pieces we've got to put together. Now, this was 10, 0. And this was 0, 5. In our first example, we had 0, 10 here, and we had 10 thirds 0 here. And you can see in each case, we are shading away from 0, 0. So this will be an unbounded region. And for a standard max problem, you're not going to have a maximum on an unbounded region. But if it's a standard min, you can have a minimum value, and that's our case here. So let's put these two regions together, find our feasible region together with the corner points. So line 1 again. XY, we had 0, 10, and 10 thirds, which is 3 1/3, 0. And we're shading away from 0, 0. Line 2, 0, 5, 10, 0. Again, away from 0, 0. And just to emphasize, of course, first quadrant, x bigger than 0, y bigger than 0. That was our original that we were working with. If you recall, that's what we had. In the quadrant 1 portion, x greater equals 0, y greater equals 0, enables us to focus on that portion. Okay, so let's make an effort to find out what's common to both. Again, shading away, shading out. 0, 10, 2, 3, 4, 5, 7, 8, 9, 10. 1, 2, 3, 4. So there's about 10 thirds. There's about 0, 10. So we have this point here, which is 0, 10. We have this point here, which is 10 thirds, comma 0. And if we draw that in and we're shading out, so we'll go ahead and do that. And I just knocked the camera, but I will fix it. Okay, so that's my first line. That's line 1. And my second line, 0, 5, 1, 2, which I'll do in a different color. 1, 2, 3, 4, 5. And then it goes all the way out to 10. So 4, 5, 6, 7, 8, 9, 10. So from here to here, that's my second line. And we're shading out. We're shading away from this line. We're shading away from this line. We are shading first quadrant here, first quadrant here. So putting all this together, what is my feasible region? This, 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 and this. It is unbounded. It's growing unbounded. So I've got no chance to have a maximum for a standard max problem, but I do have a chance to have a minimum. Now, what are my corner points? 10 thirds 0, not a corner point. This one here, 0, 5, not a corner point because it doesn't border the feasible region. This one here, which was 10, 0, does border the feasible region. So 10, 0 is a corner point, 0, 10 is a corner point. This one is a corner point. So I need to find that one by equating line 1 and line 2. So what were they? Line 1 was 3x plus y equals 10. So again, find the intersection point. Of line 1 and line 2. We only have 2 lines here to work with, so it's a little easier. Line 1 was 3x plus y equals 10. And line 2 was x plus 2y equals 10. So I'll go ahead and multiply the second equation by -3 to get rid of the x's. You mentioned enable me to solve for the y's. So the first equation hasn't changed, 3x plus y equals 10. Second equation, -3 times x, -3x. -3 times 2y minus 6y. -3 times 10, -30. So you'll notice the x's go away, 1y minus 6y, -5y, 10 minus 30, -20. Divide by -5, y is 4. Looking at the picture, that looks like it's about right. So I've got to go ahead and find x. Well, plug the 4 maybe into the first equation. 3x plus y equals 10, or a second equation might even be better. Second equation, x plus 2y is 10. Plugging in the 4 for y. X plus 2 times 4 equals 10. X plus 8 equals 10. So x equals 2. Again, looking at our picture, that looks right. So our other corner point appears to be x is 2, y is 4. So I have a total of 3 corner points here. The 3 corner points are 0, 10, bordering the feasible region. 0, 10 here, 2, 4 here, and 10, 0 here. Now, what do we want to do with those? We want to minimize. What was our original question? We wanted to minimize z equals 10x plus 12y according to all of those constraints, which we managed by looking at the feasible region. So we're going to examine those 3 critical points, 3, check that, corner points. So here they are, 0, 10, 2, 4, 10, 0. We will not have a maximum. So corner points of the form x comma y. And then we have what we're trying to optimize, z equals 10x plus 12y. And we're trying to minimize. So our corner points again were 0, 10, 2, 4, and 10, 0. So let's see, 10 times 0 plus 12 times 10 looks like it's 120. 10 times 2 plus 12 times 4. 10 times 2 plus 12 times 4 is 68. And then 10x, 10 times 10 plus 12 times 0 would be 100. So the minimum value appears to be here. So how do we write this? We would say that z obtains a minimum value of 68 when x equals 2 and y equals 4. So that's our minimum value. But again, let's go and take another look at our feasible region. This is what we're looking at. And if we want to have 10x plus 12y, x could get as big as you want, y could get as big as you want. If x is 1 million and y is 1 million, certainly 10x plus 12y is a very large number. There is no maximum for this unbounded region. So z gets as large as you want. Z never obtains or attains, which would be a better verb, I guess, a maximum value. Not that I asked that, but in those unbounded regions, you do not necessarily have a maximum value unless you have a very well-defined function. But for a standard problem that has positive coefficients, if it's unbounded, no max. If it's unbounded, you can have a minimum, as we have here. And that will conclude this lesson.